You might remember back in the Introduction to Microcontrollers course, we used a microcontroller's PWM modules to make a Cyclops eye using fading LEDs. This time, we'll take a closer look to see how it's done for an FPGA or CPLD. PWM stands for Pulse Width Modulation, and it's a type of pulse with three attributes: duty cycle, period, and frequency. These attributes convey digital information in an analog world. When sent to an LED, it will correspond to the brightness level of the LED. Looking at this example, you can see that when duty cycle of the pulse is varied, the LED becomes brighter or darker. This is the effect that we want to create using our CPLD. To do that, we'll need to use two counters. A first counter that will keep track of the period length of each pulse, and another counter to keep track of and set the duty cycle of the pulse. Using these two counters, we'll be able to slowly increase the brightness of an LED, creating a neat effect. First, we'll need to make the Quartus 2 project. We'll use the new project wizard to do that. Let's save the project on the desktop in a folder called FPGA/Lesson 8. The top level of the project will also be called Lesson 8. Then choose the EPM 3032 ATC44-10 CPLD part for the project. Click Next twice and finish the project creation. Now let's add a new VHDL file to the project and get coding. Inside the VHDL file, first we'll add the IEEE library. Specifically, we'll be using the standard logic library and the unsigned standard logic library. Our entity will be called Lesson 8 with a port that has a reset input, clock input, and 4 LED outputs. We'll name our architecture RTL, and we'll use 3 standard logic vector signals called count 0, count 1, and LED output. Inside the architecture, first we'll build the higher level PWM module with the fast counter. The reset and clock inputs are in its sensitivity list. If the reset is 1, then count 0 should be 0. Otherwise, else if the clock rising edge is detected, then count 0 should increment. Then if count 0 is less than count 1, LED output should be all 1s. Otherwise, LED output will be all 0s. This is the part which controls whether the output to the LEDs is a logic 1 or logic 0. The next process will be the slower counter. It will use the reset and clock 0 inputs in its sensitivity list. In this process, we'll also use what is called a variable integer. Variables can only be used in a single process and are much more flexible than standard logic vectors since they are not treated as signals. Now we begin the process with the if reset equals 1, then count 1 should be 0. Otherwise, else if the clock rising edge is detected, we'll perform 2 if statement checks on the variable integer CNT count. First, to see if it's less than or equal to 99. If it is, then we'll increment count 1, and when it's 100, we'll reset the counter. In all other cases, CNT count should simply increment. This block of if, else statements will make it so that after every 100 rising edge clock signals, count 1 will increment by 1. The end effect, if we look back at the previous process, is that it will take longer for count 0 to reach the count 1 value, leaving the LED output signal at 1 for longer and longer periods of time, which ultimately means the LED will slowly become brighter and brighter. Since we're only counting up, the LEDs should simply get brighter and brighter until the standard logic vectors reach their maximum value of 15 and then reset to 0, starting over and turning the LEDs off to start the process over again. And finally, we'll set the LED to LED output, and then we'll end the RTL architecture. Then save the lesson8.vhd file and compile the project. The compile goes through no problem, so let's pull up the pin planner and go through assigning the pins that we'll want to use for the clock, reset, and 4 LEDs. Afterward, recompile the design, and then go back to the pin planner to verify that the fitter set the pin locations to where we want them to be. Next up, we need to build the hardware schematic. First, we start with the power regulation circuit. This circuit has a 9-volt battery input to an LM317. 2 resistors connect to the LM317 to set its regulated output voltage to 3.3 volt. Then 2 10 microfarad bypass capacitors are added to the input and output of the LM317 to ensure proper current flow. A resistor and LED connect to the 3.3 volt output to notify that power is good. The CPLD connections first consist with the VCC pins connecting to 3.3 volt power and the GND ground pins connecting to the circuit ground. The reset at pin 44 connects to a 10 kilo ohm pull-down resistor going to circuit ground. Then we have our 4 resistors and 4 LEDs going from pins 19 through 22 to circuit ground. The clock generation circuit uses an ICM 7555 timer. Pins 4 and 8 go to power and pin 1 to ground. Pin 3 outputs directly to the CPLD's global clock pin 37. Then we use two 10 kilo ohm resistors and two 0.1 microfarad capacitors connecting in series from power to ground. We pull from 2 specific spots and connect to pin 6 and pin 7 of the ICM 7555 timer. This will create a fast clock output of a few hundred hertz. And there you have the entire circuit schematic. Now let's go build this thing up. Here are all the parts we'll be using in this experiment. The larger parts are a jumper wire kit, components kit, and a breadboard. The smaller parts from the components kit are a CPLD breakout board, LM317 voltage regulator, two 10 microfarad capacitors, two 0.1 microfarad capacitors, 5 470 ohm resistors, a 390 ohm resistor, a 240 ohm resistor, 3 10 kilo ohm resistors, 5 red LEDs, an ICM 7555 timer module, and a 9 volt battery connector. Now we'll build the circuit part by part in a fading time lapse so that you can build the circuit exactly as we will for this lesson. The circuit consists of the power regulation circuit on the right side, the CPLD connections on the left side, and the clock generation in the middle. And with the circuit completely built, connect the 9 volt battery to the circuit, as well as the JTAG programmer to the CPLD, and then finally the USB connection to the laptop computer. Open up Project 8 as we had it previously, and bring up the programmer tool. Add the .pof programming file, and then program the CPLD. And if your hardware is correctly connected, you will immediately see the LEDs transition from dark to bright, and then starting over and over and over. So now might be a good time to start pondering about how you might be able to make the LEDs dim as well as brighten. The fading effect created by outputting PWM to LEDs mesmerizes human beings quite easily, so it's a fun effect to know how to create. And we've all seen it somewhere in our everyday life. But beyond mesmerization, PWM is also used to output directional and speed data, like for motor controller applications. Here you can see a CPLD that is taking trim pot input data and outputting it as a PWM signal to a motor controller, making the motor obey its every command.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Next time, we'll explore another very fun application that uses the exact timing of signal outputs from FPGAs and CPLDs to create another fascinating visual effect called persistence of vision.